Hey everyone, so these notes are going to be on incline planes. And so the goal really here is kind of combining our knowledge of forces, talking about components, talking about free body diagrams to look at things that are inclined. So what the heck does that mean? Well, here we have a plane and you can see that it's on an incline, right? So that would be an inclined plane, but that's typically not what we're kind of looking at. We're usually looking at something more like this, where we have this box and it's kind of on a slope. And typically in kind of an AP question setting, they would give you this little angle down here. It's kind of useless unless you know a trick though, or you've just kind of memorized this one little thing. And so what I'm going to do is I'm going to be going through all of the thinking through kind of how to do this. And you don't have to worry about being able to ever reprove what I'm going to show, but you have to be able to remember what kind of our end result here is. All right. And so if we're looking at this box, and this is what you're gonna start with drawing on your own, and I would recommend you have a ruler today, actually. I would personally recommend that. Well, if we look at this, well, one of the big forces that we're pretty common and familiar with is that we have gravity acting on the box. And so there we go with our gravity, and it's just going down right there, FG. Perfect. Awesome. Got it. Then, well, if you think about it, we have this other force, our normal force, and our normal force is always straight off the surface. So if that was, what's this? So this is like 34 degrees. I don't know, maybe something like that. That looks pretty perpendicular to my surface here. And so my normal force would be going up here. And so really, if we were to like trace it all the way down, there'd be like one of those little boxes here, right? That means it's at a 90-degree angle, but we don't need that right now. So we'll just put that one there. And here is our normal force. Excellent. And then, well, typically, if this surface was really smooth kind of along here and our box was smooth, well, we'd end up having the box sliding downhill. And something that resists things sliding is friction. And so if it's resisting the motion, that means friction really would be going opposite our motion there. So here then is our frictional force, and really it should be parallel to this incline, kind of to the slope here. Mine looks pretty close, but not perfect. That's okay. And so what we got to recognize now is that we've actually made like a different little triangle right here. We have this other little triangle, okay? And so what I want to do is I want to go and put in right here a little 90, because we know that that is a 90 degree right there. That in fact is 90 degrees. And so we'll leave that there. And a triangle always has 180 degrees total between this angle and whatever the heck this angle is. And so for this last one, we're just going to name this one. We'll name this one alpha. It looks like a little fish. It's a Greek letter. We'll just use alpha. We have theta. We'll use alpha here. Now, what I want to do is this is where it kind of gets a little odd, because we get that gravity's acting straight down and friction is kind of acting up and to the right. And so in the way that we've looked at things in the past, we could have gone and don't kind of write this next little part right here. But we could have gone and said, oh, well, there's a part going to the right. So we'd have force friction in the X direction, and then we'd have force friction in the Y direction. And we could do the same exact thing over here with our normal force. And we have to do all these components. And so what I want to do is simplify life. I want to do things an easier way. I want you to be able to work easier, not harder. But it requires a little kind of challenging thinking, just a tiny bit here. And so instead of thinking of kind of like X being this way and Y being this way, what I want to do is think of things in terms of this slant. And so we have some forces that act in a direction that's parallel to this slant, this inclined plane, and we have some forces that act perpendicular to this slant, this inclined plane. And so I just want to go and take my force of gravity, actually, and you'll see what I mean by this in just a moment. And I want to go and say that, well, we can actually break up gravity. And again, you'll see this in a moment here. And let's get some green here. And that was a 34. So we'll leave it right at 34 and go something like this. So what this is doing, and you're maybe going, what the heck is going on here? I'm so confused. Well, the idea here, what we've done is just like in past units where we had like a cannonball launched at some angle and we split it into an X component and a Y component. What I've done is instead of having to split up this force and this force, we're just going to split up gravity. We'll split up gravity into a component force of gravity, and it's going perpendicular to the surface, right? There's this 90 degrees here. And so we'll call this force perpendicular, where that little upside down T means perpendicular. And then this green part then, well, this is the part of gravity that's parallel to the surface. So we'll call this one force parallel. And the two little lines that are kind of side by side, that actually means parallel, okay? So now, what I want to do is I want to take this force parallel and I want to actually go and put it right here. So we're kind of just superimposing it up there, okay? And now this is for a reason, though. So we can see that, oh, really, it's not just gravity that's opposing friction. That doesn't really make sense. But it's this parallel component of gravity that is opposing friction. And if this parallel part of gravity is greater than the force of friction, well, the box is going to slide down the slope. If the force of friction is greater in magnitude, the box is going to just sit there doing a whole lot of nothing. And so that's really kind of what determines it. Now, the beautiful thing here is that by having it drawn here and drawn here for our force parallel, the parallel component of gravity, what we have is two parallel lines, right? They're the same line that's just copied and put up here. So they're parallel to each other. And the neat thing is that gravity right here, gravity is cutting right through those two. And so this is an old geometry trick, is that if this is alpha right here, we actually know that this angle is also alpha. And it's actually because they're alternate interior angles. There's a theorem for it. We can go and you can find it over here on Google. You go and type in kind of alternate interior angles, you get this picture. And the whole idea is that as long as like line I and line M are parallel to each other, these kind of opposite, they're alternating because they're on opposite sides, but they're between the two, so they're interior in their angles. So these two are matching. They're the same angle. And so we have the same thing here. Since this one is alpha, this must be alpha. And we're almost there. We're on the home stretch. The beautiful thing is that we actually have to recognize that there's a 90 degree right there. So if we think about it, we have this kind of first triangle that was theta and alpha and 90, but now we have this different triangle, and we so far have alpha and 90. Well, that must mean, since all triangles have 180 degrees, that this angle right here must be theta. Okay, so that was a heck of a lot. I want to reiterate that you do not need to be able to go through all the thinking and proving this. You don't. What you need to be able to do is if I ever give you a problem and I go, okay, there's a slant, and on that slant there's a box, and I go, oh, and the angle here is 30 degrees, what you have to be able to do is go, okay, drop a line straight down. That's gravity. I know friction's going up this way. I know the normal force is going up this way. And then you go, okay, let's break it down. I can go and do this. And then I know for a fact that the angle here is, again, that same exact 30 degrees. That's what you have to be able to do. You do not have to be able to go through all this crazy proving and busting out the geometry there. That's not what you have to be able to do. But you have to be able to recognize and go, oh, I get what they're doing. They're only giving me this. Well, I know for a fact that that's the same as the angle right here when we drop gravity down and do that perpendicular portion. That's really what the point of all of this is, what we're trying to prove, okay? So now that you've understood kind of the thinking and how we know for a fact that the two red angles are exactly the same thing, well, you just have to know that that's it. So kind of moving on from there, well, I just want to reiterate that this F parallel, that's what the little lines here really mean, that just means it's the part of gravity that's parallel to the incline. That's literally all it is. It's like we're taking gravity here and we're finding the components of it. And we're finding the component that's parallel to the surface, and then we're finding the component that's perpendicular to the surface. And so that's exactly what this F kind of perp is. That little upside down capital T just means perpendicular. And the neat thing here is, at least as long as my box here isn't accelerating through the Earth or isn't flying off into the mesosphere, well, we know that the forces that are going off the surface, well, those must also be equal. Otherwise, my box would be kind of hopping up off the surface or going down through the incline. So that's all it is. They're just the components of gravity that are perpendicular to the incline. That's all it is. And I don't know why my L got over there. That's a little odd. There. Now, one thing I want to mention is components are not real forces. They are not. They're just not. It's literally like an imaginary thing because it's the portion of the real force. Gravity is only actually acting in that direction, down. But we can break it up into these components and we can then treat them as separate things. It's almost like there's a little force that's going straight down off the surface, and then there's a little portion kind of going along down the slant instead is kind of the idea. But these components, they are not real forces. Rather, they're really like mathematically separated parts of real forces. And though that's the case, they will affect the object as it moves up or down the plane. And for us, the main forces and components are the parallel component of gravity, the frictional force, any pushes or pulls up and down the incline, and then we just have like the normal force, really, that is related to friction, really, right? And then, as just a little final reminder, the frictional force always opposes motion. So if a box is sliding downhill, well, friction then is uphill. But if I'm pushing a block uphill, then friction, of course, is going to be downhill, right? And then again, the normal force is always perpendicular to the surface. It's not straight up like in the up positive y direction. It's always opposite the surface. So if this slant was steeper like this, well, my normal force would be going just straight off it still. So there's like a 90 there, okay? And then just last thing, if you want to use a fancy word instead of perpendicular, you could totally go ahead and call this orthogonal, because that is a synonym for perpendicular. That's really it as far as our inclined planes, and we'll start looking at some problems for this.